Assalamualaikum जनाब, मेरा नाम सरमद है. Last time we did this topic in the class, which was common source stage. For this we have this following circuit. What we have is the input is being applied onto the gate, the output is being sensed at the drain side, whereas the source is common to both input and the output side. During the analysis, we realized that the voltage gain was found to be minus GM-RD. Here the GM is the transconductance of this MOS device, which has got many expressions. The one we are interested in now is GM is equal to square root 2 mu n Cox W over L ID. Now here we observe that the GM is directly proportional to the mu n. Now mu n is called the mobility of free carriers in a semiconductor. Now why is it interesting? Why is this GM proportional to mu n is interesting for or the point of concern for us? Well, the thing is, mu n has a dependency on the temperature. Now if the temperature goes, let's say, goes up, the mu n is, which is the mobility of free carriers in semiconductors, is going to go down. And if the mu n goes down, the GM will go down. And if the GM goes down, so will the AVE. So we can observe from here that as the temperature goes up, with this circuit of common source, the voltage gain is going to go down. Now let me just put an example. Let me just put this thing in the term of in a form of example. Let's say you are working in a laboratory where the temperature is 20 degrees centigrade. You design this amplifier, which was working perfectly fine. Now you take this amplifier and you put it in a temperature of, let's just say, 50 degrees centigrade. What will happen is the voltage, well, the temperature has gone up, and you can see that the voltage gain of this particular circuit will go down. Now this is something that we don't want at all. We want to design a circuit or an amplifier which works perfectly fine for any or let's just say a large range of temperature, or a reasonably large range of temperatures. So the one of the solutions to the problem is the circuit which we are going to now is called degenerated common source. What happens is, well, the circuit remains same with a small change, and the change we're going to do is we are going to add a resistor, or we are going to connect a resistor between source terminal and the ground, and that is going to be called as degenerated common source stage. So let me just redraw this circuit here for the sake of it. So we have VD, D. From there we have this resistance RD, which is connected to the drain of the Mosfet, and from the source of the Mosfet we have a resistance RS to the ground. The output is going to be sensed from the drain side, and the input is being applied at the gate terminal. Now, so this is called the degenerated common source circuit. In this analysis, we just presume that there is no channel length modulation, so lambda is equal to 0. Now this is just assumed to make the analysis simpler. We can always have the case where lambda is non-zero. So let's move on and try to do the analysis of this degenerated common source stage. First thing first, we have to see the bias conditions for this circuit. I think it would be better if I just move my page a bit up and do the analysis on this side. Now let's just presume for the bias conditions. So let's just for the bias conditions, when I say bias, I mean there is no signal coming in. That is, the microphone is off at the moment, and all gate C's at that time is V0. So let's just see when there is no signal coming in, and if we apply a KVL in this loop, what we get is, if you apply a KVL, what we get is V0 equals to VGS plus IDRS. And well, there are two unknown quantities here. First thing is VGS, and another thing is ID. V0 is known because we have applied it from the external side. R is also known to us because this is what we have connected. ID and VGS are unknown yet. So now we've got two unknowns. It means we need another equation, and another equation that we can use is I of the ID, which is half mu n Cox W over L VGS minus VTH whole square. Now we have used this equation of ID assuming that the Mosfet is in saturation region. So now we have got two equations and two unknowns. These are the unknowns, so we can solve them simultaneously for ID and VGS. Now once we have the ID, we need to check the conditions for the device or the MOS to be in the saturation region. Now we know that if we want the device to be in MOS to be in saturation region, the condition that we have to meet is VDS has to be greater than VGS minus VTH. Now we have got VDS is equal to VD minus VS, and VGS is equal to VG minus VS. So if we take out the VS from both sides, we'll end up with VD minus VD greater than or equal to, well, they have an equal to here as well, minus VTH. So this is the condition for device to be, well, this condition has to be met if you want device to operate in the saturation region. Now let's just see what the VD and VG are in this circuit. I'm going to change my color to red, let's just say. Now let's just see, sorry guys, let's just see what VD and VG is. Now VD is the voltage here. Now we can see from here that VD is equal to VDD minus the drop that we get across the RD, and that drop is ID RD. And the VGS, the voltage over here, VG is the voltage over here, which we can see is the voltage from gate to the ground, which actually is equal to V0 when there is no input signal. And as we are doing the bias conditions, so input signal is not there, therefore VG is actually equal to V0. So let's just plug in these values back in this following equation and see what we get. Well, the VD turns out to be equal to VDD minus IDRD, and VG turns out to be equal to V0 minus VTH. So this is a condition that needs to be met if we want the transistor or the device to operate in the saturation region. So this is a condition that needs to be met if we want the device or the MOS to work to be in saturation region. Now let's just say this condition is met and the device is perfectly working in the saturation condition. Now we need to find its voltage gain and the input and the output impedances. So now that we have the circuit of degenerated common source, let's just try to find its voltage gain, its input and the output impedance. Now to do this, we need to first draw its small signal model. So let's just do it here. The device we have is NPN, and we know that the NPN has a small signal model like this. We have a dependent current source which is GMV1. Well, and then on that side we have plus minus V1. This is the drain, this is the gate terminal, and this is the source terminal. Now by looking at this circuit over here, we have the resistance RS between source and the ground. So I'm going to draw a resistance RS between the source and the ground, and on that side we see that we have a RD resistance between the drain and the VDD. Now as we are drawing the small signal model, the VDD will go to 0, because this is what we do in the small signal model. All the constant sources goes to 0. The RD is going to go from drain to the ground. I guess this is all we have got here. And yeah, and the input signal, well, the input is applied between the gate and the ground via V0. Now again, the V0 is a constant voltage, and the constant voltages are gone to 0 in the small signal model, whereas the input signal is a time varying signal. So this input signal is going to appear, whereas the V0 is going to go out. So let's just call this thing V in. So this is our small signal model for the degenerated common source. Now let's just analyze it for the voltage gain first. Now to do the voltage gain analysis, I'm going to draw a few currents on this small signal model. By looking at this figure, we can observe that the output is being sensed. It's being sensed at this point, which is right over here. So we have the output being sensed on this point. If Vout is being sensed across the RD, then the current that is going to flow through RD is given by Vout over RD. And if I apply the KCL on this node, then the current that is going to leave this node on this branch is going to be equal to negative Vout over RD. और the current, हमारे पास जो करंट यहाँ पर था जो फ्लो कर रहा है वाया थ्रू RS, obviously जितना करंट यहाँ से आ रहा है वो सारा यहाँ से बाहर आ जाएगा, because there is no other path for current to flow. So the current that flows through RS is also equal to Vout over RD. Now let's just see कि यहाँ पर हमारे पास इस ब्रांच में देखते हैं कि जो करंट फ्लो कर रहा है इस ब्रांच में वो इक्वल टू है GMV1 के, जो कि इक्वल होगा इस करंट के. So we can write down that GMV1 is equal to minus Vout over RD, which suggests that V1 is equal to minus Vout over GM RD. Let me call this equation number A. Now another equation we can see from this side is that V in is equal to V1 plus the drop on this resistor, and the drop on this resistor. This equation, I'm applying the KVL. I'm applying the KVL in this loop. So so we have V in equal to V1 plus the drop on this resistor, and the drop on this resistor is this current times RS, and the current is a negative current, which is minus Vout over RD times RS. Now this is my equation number 2. from equation number 1 I have the value of V1, which I'm going to use it in equation number B. So I'll get V in equal to minus V out over GMRD and V out over RD times RS. Now if I rearrange this equation for V out over V in, what I get is minus RD over 1 over GM plus RS. Now that thing is called the voltage gain. Now this, so here हमारे पास voltage gain है degenerated common source का. So before we go into the benefits of this circuit, let's just try to understand this equation a bit more, because we're going to need this equation a lot in the future circuits. So let's, इसमें हम देखते हैं कि जो हमारे पास denominator है RD is यहाँ पे लगा हुआ है. RD is the resistance that is tied between the drain and the AC ground, because this VDD is going to become an AC ground in small signal model. So we can say that RD is the resistance tied between the drain and the AC ground. So let's just write this thing here, that RD is the resistance tied between drain and AC ground, and 1 over GM is 1 over GM, and the RS was the resistance that was tied between the source and the physical ground, or you can say just say AC ground. So RS is the resistance tied between source and the AC ground. If you really want to see it, I can show it to you. Well, this is the RS, which is the resistance tied between the source and the AC ground. So this is a voltage. So this is a voltage gain of a degenerated common source. Let's just make a few observations here. Let's just say that if 1 over GM is very small as compared to RS, that is the source resistance that we have connected between source and the ground is quite large as compared to 1 over GM, then can be approximately equal to RS. And if that is equal to RS, then the voltage gain is going to turn out to be RD over RS, and that is an approximation here. Now this is quite an interesting expression. What happened is that the voltage gain now is independent of GM. Now this is good, because we have just learned a few minutes ago that GM depends on mu n, and mu n depends on the temperature. So now if there is no GM quantity here, so we have no dependency of the voltage gain on the temperature, which is good, but that comes at a cost. Why? Because the RS is a bit large term, as you can see from here, so the voltage gain has gone down. So now we observe that RS is a bit large term, and because RS is large, therefore the voltage gain is going to be small for degenerated common source as compared to the common source or the core common source stage. Well, this is the price that we have to pay for getting the voltage gain, which is less dependent on the temperature variations. So now that we have found the voltage gain, let's just move on to find the input impedance of the degenerated common source. Let me redraw the circuit of degenerated common source. RS, RD, and there we have the input. Now to find the input impedance, we have to kill all the independent sources. Now VD is an independent source, so we have to kill it, which means that VDD has to go down to 0. So let's just make this VDD goes down to 0, and we apply a external voltage source Vx on the input side, which lets a current Ix to flow through a circuit. Now, the thing is, our input is going to be equal to Vx over Ix. Here we can see that the gate is kind of insulated from the rest of the circuit because there's a oxide layer. So Ix is going to be fairly small. It's going to be small. It's going to be very small, or you can say it's approximately zero at low frequencies. Because this is zero at low frequencies, we can say that the input impedance is fairly large at low frequencies. Now that we have found the voltage gain and the input impedance of degenerate common source, let's just try to find the output impedance of it. Here I have redrawn the small signal model of degenerated common source, and with assuming that there is some channel length modulation, due to which we have this R naught present in this small signal model. Now, to find the output impedance, we have to follow some steps, and the steps are to kill all the independent sources, including the input signal. So we have the input signal. Now we have to kill it. What I mean by killing it is I have to short it to 0. So I'm going to put it to the ground. So what I'm going to do here is there was a wire over here. So I'm trying to find the output impedance of the circuit, for which I'm going to split this circuit into two parts. So फिर होगा क्या कि जो भी resistance इस इन दो nodes के दरमियान में आएगी, I'm going to take that in parallel with RD, and that will be my total resistance for this degenerated common source. यानी यहाँ पर resistance आएगी, that is the output resistance of this complete circuit is going to be equal to the RD in parallel with whatever the resistance that is going to come on this side. So let's try to find the resistance when I look in the circuit from here. So to find the resistance between these two nodes, I have to apply a external source Vx, and the current that is going to flow from the source is Ix. Now the Ix current is going to split between these two branches, and then this current is going to be combined together at this node, at this node, and therefore the current that is going to flow through Rs is also going to be equal to Ix. And if I look from this side, or if I apply a KVL here, what I observe is that V1 is equal to minus Ix Rs, because we have the sign plus and minus here. And if V1 is equal to minus Ix Rs, I don't know what's happening here. Well, if V1 is equal to minus Ix Rx, then the current that is going to flow in this branch is going to be equal to GmV1, and now that we have the value for GV1, therefore the current is going to be equal to G1 Gm Ix Rs. Now if I apply a KCL on this node, what I say is that the current that is entering into this node is Ix, and there are two paths for current to follow. So Ix split into two parts. One of the part that Ix split into is minus Gm Ix Rs. Therefore this part has to be equal to Ix plus Gm Ix Rs in order to have a valid KCL at this point. So now that we have all the currents defined on every branch, let's apply a KVL in this loop. So if I apply a KVL, I'll get Vx equal to R naught Ix plus Gm, that's over here, Gm Ix Rs plus the voltage drop on this resistor, which is Ix Rs. Now if I take the Ix from this side as a and put it in the denominator of that side, I'll be left with R naught. I'll be left with R naught 1 plus Gm Rs plus Rs, and well, you can also write this expression as 1 plus Gm R naught Rs plus R naught. So this is the resistance that we see between these two nodes. Or if I look from this side into the circuit, this is the resistance. This is the resistance that I see by looking into the circuit from this side. So remember, there was another resistor over here which was RD, and the total total resistance, or R out, of degenerated common source is given by R out equal to 1 plus Gm R naught Rs plus R naught in parallel with Rd. So this is our output resistance. So let's just do an example, just an exercise. This is example 7.10 of your book, where we have got two Mosfet devices, M1 and M2. M1 and M2 both are biased with the different voltage levels V and VB, and we have assumed that these two devices are both in saturation region. The question is to find the R out, which is this resistance R out. So let's just see how do we move about it. Now if I look carefully over here, what I see is this part over here can be thought of as a current source. And we know that the current source has a small signal model of this, where the current exits the node and enters into the ground. This is because we have got the NMOS here. So now let's just redraw this circuit with this part being replaced with R naught 2. The 2 comes up because of this M2 MOSFETs. So we can redraw this circuit as follows. अगर हम इस सर्किट को केयरफुली ऑब्जर्व करें तो what we realize is this is more or less like a degenerated common source. वहाँ पे RS था सोर्स के साथ, यहाँ पे सोर्स के साथ R02 लगा हुआ है. So if I remember correctly, वहाँ पे हमारे पास, well, additionally there was an RD over here. RD यहाँ पे नहीं है. So what we can see is कि हमारे पास जो आंसर है is going to be something like this without the RD. So हमारे पास जो resistance आएगी, हम यहाँ पर देखें output resistance, that is going to be equal to 1 plus Gm. Now that is going to be Gm of this first MOSFET. So I'm going to put a 1 over here, and R naught, and that R naught is going to be of this M1. So I'll have R naught 1, and that is going to be times, in place of Rs, now we have R02, so we'll have R02 over here. So this is the resistance that we get for the case of this circuit over here. So that is all on the degenerative common source. Thank you for listening.